Hello everyone, this work is titled The Inefficiency of Interaction and is about the abstract machines inspired by geometry of interaction and game semantics. This is joint work with Beniamino Accattoli from Inria in Paris and my supervisor, Ugo dal Lago. We set our analysis in the simplest possible setting, closed call by name lambda calculus. That is to say that our terms are pure untyped lambda terms and there are no free variables. This way, abstractions are the only values. The calculus is the following. Terms are formed by variables, lambda abstractions, and applications, while evaluation contexts are just the whole or a context applied to a term. Beta reduction is the usual beta rule applied inside any evaluation context. Already in this very simple setting, beta reduction is not an atomic operation, and so how to implement it is non-trivial. Abstract machines were one of the tools that appear in the literature to tackle this problem. In particular, the literature from game semantics, geometry of interaction, and linear logic influenced the design of several abstract machines. The first one to appear was the interaction machine, dubbed YAM, and devised by Jan Maki, that was directly inspired by the geometry of interaction. In particular, it was a very simple compilation schema for the language PCF. Highland and Dong game semantics instead inspired a different abstract machines dubbed the pointer abstract machine or PAM, that was directly crafted after the intuitions behind game semantics. These machines were put together and compared by Danos and Renier, and in particular it turned out that the machine behind Highland and Dong game semantics could be obtained just with a little variation over the machine by Maki, doing a very simple optimization. However, the comparison between these two machines was done only qualitatively and at the level of a graphical formalism, without any formal reasoning nor any quantitative analysis between the efficiency of the two. We compare all these machines obtained from game semantics, linear logic, and the geometry of interaction with a more classical machine, a machine based on environments, that is the machine by Cruvin. This machine has been studied a lot and its complexity and efficiency is very well known. Why are these machines so interesting to study? There are two main reasons, and the first one is that they led to space-efficient computation schemas. For example, Maki devised a very small runtime system for PCF, and this compilation schema turned out to be very space-efficient. Secondly, Dan Gika used ideas from the geometry of interaction and game semantics in order to give a compilation schema for higher-order languages directly to digital circuits that have, by definition, a finite amount of memory. Finally, Ugo dal Lago and Ulrich Schoep used ideas from geometry of interaction to devise a functional programming that is constrained to work in log space, in the spirit of implicit computational complexity. The second reason instead is that these machines are behind the denotational models given by game semantics. They are the computational backends of game semantics, and in particular the interaction abstract machine is the mechanism behind Abramsky and Kotos game semantics, while the pointer abstract machine is the mechanism behind Highland and Dong game semantics. This way, studying these machines and studying the efficiency of these machines amounts to study also the efficiency of the denotational models in some way. So we briefly present what our work is about. In the first part, we give a complexity-aware taxonomy of the different abstract machines based on game semantics and the geometry of interaction. We have redefined some of them from the literature in a common framework. Then we have proved them correct in a uniform way. And finally, we have compared them and ordered them with respect to their time consumption, thus stating clearly their efficiency. In the second part of our work, we give a type-theoretic understanding of the interaction abstract machine. First of all, we define a new version of the interaction abstract machine on top of intersection type derivations. Then, we prove that this new version is actually equivalent to the traditional presentation of the interaction abstract machine. And finally, through a quantitative analysis of type derivation, we can give a semantic measure of the YAM runtime. So, let us talk briefly about the structure of our abstract machines. In particular, all the abstract machines of this paper are token machines. This means that we can think of them as a token that travels around the program under evaluation carrying some information. The position of the token inside the lambda term is represented via a pair formed by a term and a context, and of course the term plugged into the context always gives the term under evaluation. For example, on this figure we have that the token is placed just inside this lambda abstraction, and so its position is represented by the term t and the context lambda x dot whole. A state of the machine so is typically given by the position of the token together with its content, that is some auxiliary data structure that we call S. Transition rules of these machines are thus in the following way. A position of the token and a data structure evolve to another position and a different data structure. This way we have a typical automaton-based representation of abstract machines. In this slide, we see our main results about the relative time efficiency of the different machines. In particular, we proved that the YAM is at most exponentially slower than both the JAM and the PAM. The JAM and the PAM actually are isomorphic, and these two machines are at most potentially are quadratically slower than the machine by QV. All this picture is particularly interesting because since the YAM is the computational backend of Abramsky game semantics, this means that the computational mechanism behind this kind of game semantics is particularly inefficient. Instead, the JAM and the PAM are the computational mechanism behind Highland and Don game semantics, and thus they are polynomially related with an efficient schema like the machine by QV. In order to obtain these results, we used a uniform proof technique, and in particular a bisimulation-like argument. Thus, correctness of all these machines is a byproduct of these bisimulations. We were able to build these bisimulations between any of these two machines thanks to an inductively defined invariant that we spell out for any of the different machines. The fact that all our proofs were inductive in nature let formalization be in principle possible. We do not have done it, but we plan to do it in the future work. In the second part of our work, we give a type-theoretic understanding of the efficiency of the interaction abstract machine. In order to explain what this type mean, we give a very brief explanation of type systems. So we start with simple types for the closed call-by-name lambda calculus. These types are formed by just an atomic type star or arrow types. It is well known that simple types are sound for termination. That is to say that if a term is typable with star, then this term converges. But these types are not complete. For example, it is not possible to type the term lambda x dot xx, but of course is convergent since it is a normal form. If we want to capture termination, we need to move to intersection types. This time, types are formed by an atomic type star or an arrow between an intersection of types and a type, where an intersection of types is simply a set of types. It is well known that intersection types are sound and complete for termination. That is to say that the term t is typable with star if and only if the term converges. However, these types are qualitative in nature and cannot give any dynamical information. For example, we cannot infer the complexity of the reduction. In order to recover quantitative information, non-idempotent intersection types were introduced. In particular, now we have linear types that are, as before, an atomic type star and an arrow between an intersection type and a type, but intersections now are not anymore sets of types, but sequences of types, and thus types can occur more than once in a sequence. That is, intersection now is no more idempotent. Again, non-idempotent intersection types are sound and complete for termination. Non-idempotent intersection types are nothing but another way of seeing the linear logical, operational, and denotational semantics of the lambda calculus. So they are deeply connected with all the other ways in which this connection can be seen. So, for example, from the operational semantics, we have the linear substitution calculus, which is isomorphic to the reduction of proofnets, or we have the abstract machine bioquerying, and also the interaction abstract machine bioquerying, and moreover, polyadic calculi, polyadic approximations of the lambda calculus that takes resources into an explicit form. From the denotational point of view, we have a relational model of linear logic that is deeply related to non-idempotent intersection types, in that it is just a semantical way of viewing the very same thing. Indeed, the set of non-idempotent intersection types that can be given to a term is just its relational semantics. Finally, also game semantics, denotational models, comes from the linear logical understanding of lambda calculus. So all these different approaches are just a different way of seeing the very same thing, that is the linear logical way of understanding lambda calculi. Linear logic has a deep computational meaning, and in particular it takes into account resources. And so in the very same way as linear logic refines intuitionistic logic with quantitative information, then non-idempotent intersection types refine intersection types taking resources into account. And in particular, the fact that intersections are not idempotent allows to not lose any information. They allow to ease completeness proofs, since simple inductions can be used, for example, to prove soundness and completeness, while for traditional intersection types the reducibility technique was needed. Moreover, type derivations of intersection types can measure the complexity of lambda terms, also according to different notions of evaluations. This has been done by De Carvalho, Delia Kessner, Beniamino Accattoli, Stéphane Langrand, and others. These are the inference rules of our type system and are quite standard because they are the same of the original system by de Carvalho. Please note that abstractions can be typed in two ways, with an arrow when they are in a functional position and with the atomic type star when they represent a value. And in particular, normal forms are values, and so normal forms are always typed with the atomic type star. Our intuition was that we could build a machine isomorphic to the YAM on top of intersection type derivations. And in particular, given a type derivation ending in star, so given a term t typeable with star, we can consider a token machine that starts from the root occurrence of that term. So one can move from the root occurrence of star in a natural way inside the derivation, following in some way that occurrence of star. The obtained machine is actually strongly bisimilar to the interaction abstract machine, and we have proved this fact through an invariant that is of the very same nature of the ones used to prove the correspondence between the different abstract machines presented in the first part of the talk. So in this way, in this new machine, states are represented by occurrences of star in the type derivation of the term. We can see in this slide an example of a typed term with its type derivation, in which all the occurrences of star have been marked with some increasing numbers according to their states. So the star numbered with 1 is of course the first state of the machine, the star number with 2 is the second state, and so on. So we can see that in this machine the token travels around the type derivations following the different occurrences of the atomic type star. So states correspond to star occurrences, and since it can be proved that there are no cycles in these machines, then the number of states is actually the number of reachable states, and then the number of states becomes the runtime of the machine. And so in order to compute the runtime of the machine, it suffices to count the number of stars in a type derivation. So we have that the runtime of the machine on a given term depends not only on the size of the derivation, but on the types that are present in the derivation. Instead, for the machine by Krivine, which is efficient, and we have already seen that can be exponentially faster than the interaction abstract machine, runtime does not depend on types, but depends only on the size of the derivation. So if we have a term t that is normalizable, so a term t that in n steps reduces to an abstraction, we have that types of t can be actually exponential in the size of t and in n, while the size of the type derivation for t is at most polynomial in the size of t and in n. So we can understand from a logical point of view, from a type theoretic point of view, where the exponential gap between the interaction abstract machine and the Krivine abstract machine comes from. Thus, YAM inefficiency comes from the use of higher order types. Our work was only the first part of a general study of the efficiency of game machines, and in particular it was a study of the time efficiency. We are devising a type system that takes YAM space consumption into account. And this is highly non-trivial because the type system that we use to compute time consumption does not give enough information to compute also space consumption. And so we have to redevise the system in order to compute also space. And this is currently a work in progress. And moreover, we are investigating if the YAM could be a reasonable cost model for time and space. So if the YAM could be simulated by Turing machines and vice versa with a polynomial overhead in time and a constant overhead in space. Thank you very much for the attention, and see you in the live question and answer session. Goodbye.